Okay.
Hello, everyone. We're going to present today a project that we call From Reasoning to Superintelligence, an RL perspective. So the original paper was called A Search Theoretic Perspective. We're going to look at some RL things, and we derived some things we hope are going to be useful to the class, maybe. What next? The trees, okay. So last time we looked at things like supervised learning, where we just have a question and we directly get an answer. So maybe this was X, this was Y, supervised learning. Then we said that chain of thought might perform better when it generates these intermediate steps. From the question, intermediate steps to Y, chain of thought. And then this paper, the original one, presented tree of thought with backtracking. So that means we generate some chain, we realize it's wrong, we go back, we generate something again, realize it's wrong, and then we arrive at the answer, perhaps. I'll call this tree of thought with backtracking. Now, we're gonna kind of frame the reasoning problem as an RL problem. So let me define maybe the MDP. So it's gonna be an MDP Markov decision process M, which has states, that's wacky, that's actions, set of actions, a reward function, a deterministic transition function, a finite horizon, and an initial state distribution. So we can say that the set of states is some like conceptual reasoning steps. The set of actions, similar like this, it's just going to be some, like appending some thought, changing our conceptual reasoning in some way, some like thought direction. The reward, we're just going to define it very simply. It's just either 1 or 0, depending on 1 if S and A solved it. Like answer the question, solve the problem, 0 otherwise. That's very simple. Then a finite horizon will assume that we only need H number of steps to solve the problems, and an initial state distribution, which is like some well-formed problems. So in RL, we usually want to learn a policy pi that takes in a state, and we'll consider a deterministic policy. It just predicts us a single action. So we want to learn a policy that eventually gets to the positive reward. That's usual in RL. So we'll define a value function, which is also pretty standard under the policy pi. It's just going to be an expectation, taking actions with respect to pi, sum of the horizon, maybe something like that, R of SA. SH, AH, and S0 is the thing we predict, pretty standard. And then maybe the quantity of interest we'll want to bound, which is what our results are gonna be written in terms of, is this J, which is just the expectation of the value function. With these states drawn from the distribution of states we obtain by following that policy. So this is what we're gonna find, and we got this table. We're gonna show results for behavioral cloning, something that's like standard, what's the quantity of interest is like, and then write something for the diligent learner, which is our version of the algorithm they propose, except in RL terms, and then maybe an extension which is having this suggester, which we'll explain later.
I have a question about the J5.
Yes.
So like, if you have an H horizon MDP, you're like 1/8 of the time at stage 1 and 1/8 of the time at stage 2 and so on. So what is this d pi thing? Capital pi? It's like the the probability of occupying a certain stage, or state?
This one.
Yeah, what is that thing?
Yeah, we haven't actually taken a look at that. It's just a.
Isn't it D0?
Yeah.
Didn't you want to write D0?
Like usually
Yeah,
it's from the
initial
start state.
distribution.
Perhaps it's D0.
I would think so.
In my notes it's D pi, but I think it should be D0.
Yeah, then it would make sense.
Yeah.
But
I
it
didn't
could,
think
But
about
it's
it.
under policy
normally
pi.
it could be under the.
Oh, no,
It's
in
under
a
policy
V,
pi.
there is, in the V, there is a pi already, so like,
Fine.
what do you mean? It just, initial state is drawn from D0,
But you could
apparently of any pi. Problems are given to you from D0, and then you solve
But
them.
you might want to.
But it could also be under like a different policy's occupancy, right?
Yeah.
But like,
Yeah.
why would you do that? Like, someone changes the problem distribution for you?
It's like policy evaluation.
No,
kind
it's
of.
Because you
like
can
you're
add what
trying
you
to
see.
solve fix the distribution of problems. That's the setting of that paper, right? Like,
Yeah, no, I agree,
so
with
then
that.
why complicate? Just move on. It's
Yeah,
D0.
we will get into
Okay.
that discussion. I think there'll be some
I
things.
have some other question though. Clarification question about this reward.
Yes.
So you can have multiple rewards along a trajectory, like,
We can assume that if we reach the 1, then the episode terminates.
then you go to a terminating state and you get 0 reward from that point
Yeah.
on.
And, yeah.
You're terminating.
Yeah.
Okay, alright, because then it really maps to problem solving, otherwise it wouldn't really.
Yeah. So
Okay.
then, what you said and this, we would think that there's some optimal policy, pi star, and maybe j of pi star is going to be equal to 1, because it's always taking the right path.
Mhm.
This is just a simplification we use in our proofs. And then the standard result, which is taken from prior work from 2010, it says if we have a pi, a policy that has these conditions, which are that the probability, if the states, wait, this is wrong. The states come from d pi star. So now the discussion, you were saying policy evaluation versus, so this says if the states are coming from a distribution which is induced by following pi star, there's a asterisk there. That means it's important or hard to understand. Equal or, yeah, I'll write equal here, but the optimal policy might be like have multiple solutions, so maybe I should write this. Yeah, this is like abusive notation maybe. Let's assume there's one path or multiple paths. Maybe it doesn't matter that much. We just assume that this probability is greater than this. So there's some error. And with probability of this, it's not gonna take the right action, but with this probability it's gonna take the right action. And I think then the result is that this j of pi, if we have this assumption, then it's like 1 minus h epsilon. I think that's what's standard, and this is
H squared, I think.
h squared, maybe.
It is.
Maybe. I think in our results as well, perhaps.
It is
Maybe.
definitely H squared.
Yeah. And this is us. And back of that. 2010. So that's what's standard. Yeah, and now we want to maybe improve this number. We don't know whether that square is there actually.
It
It
is
is.
squared.
It is
It's
there?
the covariate shift distribution, right? Because of behavior cloning, they address the behavior cloning problem. So it scales with epsilon t square, which is horizon square. Yeah.
Okay, I wasn't following that. Let's say it's, yeah, it's probably right.
It is there.
Okay. But then our diligent learner, how we're gonna define it, is gonna maybe consider, that was one result. That pi star is maybe from states to multiple actions, like I said, maybe it's this case. Like there are multiple solutions to a problem, so we can take multiple paths from the initial state. And now we're introducing this new pi prime, which is given a state, we predict let's say, B actions. Maybe that's an ordered set, and we're gonna use that later. And you're gonna tell us how we're gonna use it?
Okay.
Right?
Okay. So, let's say this is the situation for the behavioral cloning setting, and now we're gonna talk about this diligent learner. So,
What exactly what do you mean by, what is a behavior cloning setting? That's specific, sorry. How does that result work? Like, what data do you have, what are you doing?
So we just assume we have a policy that is this good, and if it's this good, then this J is gonna be this good.
Oh,
We are hiding the
I
detail
understand.
of like, how do you get that policy?
okay, got it.
And we'll actually, like, we'll also just state assumptions without
Okay.
actually showing how these assumptions hold.
I get it.
So that's for the next couple of
Mhm.
weeks.
And the policies are deterministic, right? Because
Yeah. We didn't want to, we had a suggestion that we shouldn't get into the stochastic policies to make the analysis simpler,
yeah.
That's a good idea.
and maybe we'll do that in a couple of weeks or months. If we have the time.
Someday.
Someday.
Yeah, I mean, keeping it simple is a good idea.
Yeah.
yeah.
Mhm.
So now we have a pi prime. And let's say, so we wanna do this. So this should be familiar.
What happened?
No.
You wrote the same,
It's the same thing. We need to,
you wrote the exact same.
Oh wait, no.
it's.
Oh right,
that-
right.
that thing.
Oh,
I wrote the wrong thing.
Yeah.
Oops. Okay. Okay, right. So what we actually want to say, since we can have these multiple possible actions.
Yeah, our policy predicts multiple actions, and our goal, like our optimal policy also has multiple actions. So here we're saying the probability that the action that we produced from pi prime is in pi star for all i's in the B actions we generated is greater than that number.
So it's a subset. You're saying that pi prime S is a subset of pi star S.
That's not quite what we want to say.
What? Yeah, that's what you wrote.
We want to say that, actually there should be,
Well, I don't know.
yeah.
I don't know
We
what that
didn't know how
means.
to write it, we wanted to mean something else, but we wanted to mean that each AI generated from pi prime has the probability of being good with that probability.
Yeah. Before that, this pi prime, it maps to A to the power of B. What do you mean by that? What's that?
So it generates B,
Awesome.
possible
Options.
options.
I see.
Yeah.
I see. And so you want to say, like, what fraction of the options is good?
No, we want to say that,
All the options are generated are good?
yeah.
For each option, there's this.
No,
Yeah.
like, you wanna say all the options are good.
Mhm.
Yeah.
But maybe
Yeah,
it's like
this.
there exists an I. That's
No, that
no.
would be very weak.
Mm.
Maybe we should have written like maybe here for all I in
B,
B,
This is true there.
each AI is,
which would be the same as saying that pi prime S as a subset of A is a subset of pi star S.
no, but that says that all of them,
Yeah?
but we
What
want-
else are you saying? Are you saying that some of them are not good? Which one? How many of them?
Yeah, not how many, we want to say that each one is that good.
Yeah, I guess it's.
So
comes
if
to the
each
same-
one is good, then everything that you generated is good. That's just, it's the same word saying the same thing. That just means that it's a subset.
Mhm.
I think
If
it
each
does-
one of them is good, are you saying each one of them is good? I believe you're saying that.
Maybe
because that will lead to a result. If you would only say that some of them are good, that would be too weak.
Yeah.
Because when you start to follow pi prime, let's say uniformly distributing your mass on whatever suggestions they are, or like searching, then there's branching, right? Like on one branch, it's all good, but maybe only one branch, and then there are so many other branches, and then you have a big search tree. It's exponentially sized in age, and you would be in trouble. The way to prevent that is that all the options are good, sure.
Yeah, and I think we're thinking of it option by option, but that does come to the same thing.
We wanna say that
Saying
like,
the whole sub,
if
it's
we,
a
if
subset
we
of the correct options.
take one action one, it will have this probability of leading us to the next correct thing.
Wait, is there something random there in the transitions? Why is there a probability involved?
No, we're just saying that there's a fraction, maybe this is the fraction of states that we might be wrong at. Maybe
Right,
that's what we
okay.
wanna say, yeah.
And then that would mean that whichever action you're taking
Yeah.
from the suggestions by pi prime, the fraction of states on which you are not taking good action is at most epsilon prime. That's what you're saying.
Perhaps.
That means that, well, I just tried to repeat what you were saying.
Yeah. So, yeah,
So that would be a subset.
okay, you can write a
Yeah.
subset maybe.
Yeah,
Maybe that's
okay.
fine.
Okay, let's
Yeah.
keep it up as this for now, but it's the same thing as it being a subset. And we also want pi b, and that's gonna be,
Oh, I didn't define that.
Is that a different b than above?
Yeah,
um,
we're gonna need something else.
yeah.
We're gonna want.
Can I ask, why is pi prime not mapping to 2 to the a? What's special about, like?
Yeah, it should
always-
be.
It
Yeah, it's
always,
unnecessary complication.
it's
Right.
always of, at most
It
b
says-
things.
It should be,
Yeah, it's not just a list of actions, but it's the same thing as suggesting a subset of actions if you don't care about the ordering of those actions that is
Yeah.
suggested. Are you going to care about the list?
I mean, this is also exactly b actions,
Yes.
which is weird.
Well, it can recommend the same action multiple times. No one said that,
Yeah,
so it's a subset of at most cardinality B.
Yeah.
or maybe the
Oh, right.
intersection. Maybe what we mean is that the intersection of those two has the probability of this.
I mean, there is no probability involved, right? Because they are deterministic policies. Given a state,
Yeah. But
you would have an intersection or no.
yeah, it's a fraction. We can move on, we don't have much time actually.
Yeah.
Yeah,
Okay.
there is
Okay,
much
let's-
more to this.
Yes.
The details,
Yeah.
yeah. We'll
I
figure
mean,
it out.
it will be important, but
Change the probability.
maybe this is not the main thing
We
then.
can continue with the vibe.
yeah, this is just the assumptions for the main part.
So what's happening?
So we want a pi b such that the, yeah,
What is I and I star?
Okay, so here we have to maybe explain it in words.
yeah,
So the backtracking works like, when we're at this state, the set of states we can backtrack to is different than if we were at here. Like from here, we can backtrack to this one or that one.
Oh, this is about the backtracking.
yeah,
Yeah.
that's this b.
I had no
It's
Yeah,
backtrack.
and we say that this policy is like from states to states, maybe. It just gives us a state where to
It's
backtrack to.
also a B, but it's a different B.
This is a different b, maybe we
can-
can
I
make
do-
it
It's not really a policy, it's like a mapping back to where.
Yeah.
Well, whatever, you can call
We're
it a
gonna use it
policy.
as a policy kind of.
Oh.
So this I is like the time step or like the.
When
yeah.
we are taking
Yeah,
Yeah,
the backtracking action.
yeah,
Yeah.
And what is I star?
So this just.
This is the
Oh, that's
optimal.
I, and then there is a star, that is
Yeah.
an optimal backtracking.
Yeah,
Yeah. We need to work on the notation.
I
No,
is
you
the
just have to
destination,
explain.
right?
yes, so,
No.
We didn't let you explain. so please.
So the I is the time step. So at each time step, this pi is gonna have different options to backtrack to.
Okay,
Yeah.
So we're just saying that at each time step, the probability that we get a correct backtracking step is this.
uh-huh.
Does that make sense?
Okay.
And what's the definition of the optimal backtracking guy?
Yeah, we did not define that.
I think right now we're saying it's the last correct step that is known to this.
Maybe we can say that where the value function was still one for the optimal policy,
Right, like not a dead end.
not a dead end. Yeah.
Okay.
And then if we have those two assumptions, then I can do the algorithm. Then if we have those two assumptions and this algorithm, then we'll get some result. But first the algorithm. Procedure. So we get a state. For this state, we get these, let's say A is the set of actions that we get by performing this. So we get our set of actions, or we kind of get this A from memory. So that, like it's a set, and we will like pop one action from it, and then maybe do something, and then if it fails, we pop another. So maybe here, I'll say pop an action from this set. Then we go to the next state, just transit. Maybe I needed to say T plus one. T action, T. Then we just get the reward, which is usual. T. Then if the reward is 1, or the horizon is exhausted, then we just return, let's assume this has the trace, it kind of returns us the trace that we obtained following this policy. I will not like write out the full thing. But if we didn't finish an episode, then we get this other action, which is kind of a state from this B at time step T plus 1. So this is where we call this function.
Uh-huh.
So it gives us a state to backtrack to, perhaps, and then we check if
It's an SB, or like I can't read it, like what's the letter that you're backtracking to? What's AB?
AB, just like.
And that denotes a state. The AB denotes a state.
Yeah.
Okay.
So if it's equal to the current state, yeah, notation needs work.
Yeah. Okay, fine.
Then we just return diligence act that's T plus 1. So that means we just continue the same thing on this new state. Otherwise, we continue from this new state. Let me write this out.
Well, it seems that either way you are going direction
Yeah.
back on whatever is returned, so you don't need if.
Yeah.
Do you?
Do I need what?
The if
You
is
can-
unnecessary, it's redundant. In both cases, whatever was returned, you're
But it's
calling
like, it's
digit
good
back on it.
verbose code, you know, for understanding what's going on.
Yeah.
Yeah,
I
let's say
mean-
we just wrote this out for you guys.
Okay.
This is how I program.
And then this gives us something?
This gives us something
Yeah.
that we don't have time to prove, but this is hopefully correct.
So then it'll be also h squared, I think.
Yeah.
Perhaps.
I think.
Yeah.
So we got h maybe squared.
Uh-huh.
And inside we have our epsilon prime, and we have a bunch of things subtracted from the list. Okay, so this is one. And this is a sum. Okay, so over here, we have the same structure as this, but this term, we can see this is greater than 0, this is greater than 0. We can say this is going to be greater than 0, this is also greater than 0. So this whole thing is greater than 0. This will be smaller here, so
So just improving the thing.
How does epsilon prime relate to epsilon?
Can't we sum this? It's a geometric series.
yeah,
Let's
we
sum
can.
it.
I think we had it as the sum and then we put
So
it back as
if you
this.
don't write
'Cause it
this
doesn't
one
really
minus
simplify.
one minus format, but you
Yeah.
just say that the suboptimality in the first case is
Yeah.
8 squared epsilon. In the second case is 8 squared epsilon prime minus something.
Something, yeah.
Then it makes a lot more sense rather than saying double negative like 1 minus blah blah blah.
Yeah, this,
Okay, so let's
this
do
stuff is
it.
kind of,
And then let's sum it up to see what is going on.
yeah.
What
So we can write also, give me like this, I star minus j, this, right? We do that.
This.
And then you
No.
just write h squared epsilon here, and then h squared.
It's the other
minus-
direction, but whatever, less than equal.
Oh, yeah,
If it was greater than equal, that would be bad news.
yeah. So you want me to do this now?
And this,
Yeah, exactly. Let's try it, and then
Let's
try
get
to
like a
try to
couple.
sum that thing, because
We did try that out, it didn't really help us,
it does.
does it?
Or it doesn't, because
It doesn't
under the
simplify.
exponent, you have epsilon prime times 1 minus epsilon
B.
b.
Yeah.
Still, let's sum it.
Alright. One.
All of this will be to the
Yeah.
power, and then this is 1 minus. Does that make sense?
Yeah, I think it does. And so you can surely ignore the, but, okay, there are B options. Okay, so that's what your branching factor or something. And then,
This was yesterday's midnight's
Yeah,
results, so
yeah.
we don't have much.
well, we can surely drop this exponentially small term, like just think
Yeah.
about that at just order is 0. So then you have 1 over 1 minus epsilon prime, 1 minus epsilon, right?
Why don't you use the same epsilon?
No, not yet, but maybe one day.
Just to
But-
show the relationship. how-
Or coefficient, you know?
But we can approximate, so after you drop the complicated term, you have 1 over 1 minus tiny. 1 over 1 minus tiny is like 1 plus tiny, right?
So you mean.
So we can
Plus.
approximate that thing, yeah.
Good.
Yes.
The epsilon
And then
prime.
let's see what comes out. Well, okay, so the tiny was epsilon prime times 1 minus epsilon beta,
Mhm.
okay? So this is 1 plus epsilon prime, 1 minus epsilon beta, and then that's multiplied with this 1 minus epsilon prime, okay? So the main term,
This is all.
I'm afraid this is going to be negative. Like after you subtract it from epsilon prime, you get something negative for epsilon prime. It's like,
Uh-oh.
doesn't look great, because the main term is 1. And then there is some epsilon primes,
Mhm.
and then you're subtracting away the epsilon prime, and then you have a minus 1, so something is missing, probably some epsilon prime multiplies this other thing.
So the error is negative, that means we're.
Yeah, you're very good,
We're
right, you're
very
doing better. Yeah, I shouldn't phrase this as bad news, although who knows? Yeah, something is a little bit off, but it's definitely interesting.
What is the relationship of epsilon and epsilon prime in the two cases?
So epsilon just talks about,
Well, you could choose maybe the same, right?
this error.
Because one is matching.
Just one deterministic action, and this epsilon prime is like, we can say that there
But
is.
if you change prime to be like b equal to 1, like sorry, if you change b equal to 1, then it's the same as that previous case. Oh, maybe not. Then you have to change
Actually-
that stuff. Like I'm just wondering what's the well, how do we interpret these two results? One of them
Actually,
is epsilon.
what I think now is that instead of having pi prime, we just have b of these that are different, and then it would be the same epsilon, right?
It will be b times epsilon, right? Like 1 minus b times epsilon.
Yeah, each of them can make a mistake.
Yeah.
Different sets, they make a mistake. But like, okay, too many things. So if you had b of those, you are asking whether with backtracking you could improve upon the b times epsilon bond that you would just get from the Ross and Bagnall result. You don't know which of these is the correct one, then you could randomly choose one of them and follow it. Then you would get the b times epsilon bond. Okay. Now the question is whether with backtracking you could improve on that.
So we think that
Good.
backtracking comes into some, and we need to do something here to make it nicer. But what we thought is that if these epsilons are the same,
Mhm.
this epsilon is just like something smaller, because we subtract something from it.
Yeah.
So it's like slightly better. But we don't know.
That would be a good direction to go.
It doesn't do away with this h squared. Maybe we should do something here. So during our work yesterday and before yesterday, we didn't get this squared. Maybe we just missed it. But everything was
easy.
just h something, and this was also h epsilon.
Yeah.
But that's where we got.
We also have one more thing,
But we have 3 minutes.
3 minutes. Okay,
Yeah,
We
speed
can just
run.
write the result.
Okay, yeah, let's just write
So
it.
for the suggester, I can explain. With the suggester, we assume this policy, so it just predicts one thing. But the suggester now kind of, it's like an out-of-distribution detector. Whenever it detects we're out of distribution, it just immediately kind of gets us a new node. Like, if this was like our starting point, we went down a bad path, then this new suggester kind of says, okay, we're at the bad thing. It would immediately kind of jump us to something that's good, and then we continue.
But
following
if
this.
it puts you back to the initial state, then this doesn't help you at all.
It doesn't help because the policy will still predict that thing.
Right. So then how are you expecting the suggester to do anything good?
So the suggester just gives us a good state.
Yeah, but like the initial state was a good state.
The initial state was a good state, but our policy didn't take a good action.
Sure. But what prevents the suggester of suggesting the initial state as a good state?
We don't know.
If you don't make any assumption about nothing, well, you probably make some assumption about it, and then that's ruled out, then okay. So, but the idea, like, what would be the idea of the suggester? It somehow helps you to move forward when you're at some bad spot,
Yeah.
Yeah.
right?
So yeah. In our case, we just. I know we.
But the suggester would be called during your search procedure, or like, or somehow.
We have another algorithm.
I think it's very similar to this one. We wouldn't have this line, or we would have something like, instead of these two, we would have just ft equals pi st. This is the same. This is the same. This is the same. Here. So this would be the suggester. It would give us. I think it's just the same thing. In some sense. Did we change anything? I think we didn't change anything.
Well, pi is pi prime becomes something that goes just to one. It doesn't give us a set of states.
Yeah, so that's this part, so,
Yeah. And then
but then the rest is the same.
we have the suggester,
I forgot.
which doesn't need to
I think we could
backtrack
just
with some error, it just goes directly to the.
suggester.
So basically, suggester knows what action to take from ST to get
Yeah.
to an optimal ST plus 1.
Yeah.
So suggester
If
is.
it was not at the end.
Yeah.
Right. If there is a way up, then it would suggest a good action. And it moves you forward, not backtrack. The other guy was like, oh, let's move back
Yeah.
from dead ends. That's important. But if you're not at the dead end,
Mhm.
maybe you're not taking good action, but you could ask someone like, what is a good action from there? So maybe the suggester is doing that.
We have something like.
Yeah.
I think Ross and Bagnall
I think,
consider that.
You're thinking of it as moving at the same level,
Uh-huh.
usually.
I think the suggester is like the dagger algorithm for behavior cloning. So there is an oracle that, so when you're going out of distribution,
Mhm.
it pushes you inside the distribution somehow, if I remember correctly. So I think what Chava said, it suggests what action to take when you're stuck in a bad state, if I'm not mistaken. But yeah, I think it's like,
Sounds
Something similar,
very
yeah.
close to
Yeah.
that to me too. So you
Mhm.
look up dagger from this guy. It's in the same paper.
yeah.
So suggester is like an external source of information, right?
Yeah,
Mhm.
Okay.
And so is the backtracker.
yeah.
But then we just stated these assumptions, now we need to, I guess the next step is like, maybe showing a training algorithm that would make this hold.
Mhm.
Because this also had the pi star, this had the p prime, and that's a discussion we started at the start and didn't finish.
Yeah.
Like the one policy that's taking the actions, like going down the tree, needs to be
Right.
good under the optimal policy. But this backtracker needs to be good under whatever that thing is doing.
Yeah.
So I think that was the coverage thing we discussed in the lecture. And we didn't get there yet. We might get there. So, yeah.
Sorry. I'm a little confused about that B branches that you're making. I think the point of that is just, it should be like, for example, at least one of them is good. Not all of them is good. If all of them is good, why I'm making B branches? I'm kind of exploring, and if at least one of them is good, then I can kind of go forward from that children. Why you're suggesting that all of them should be good?
No, I think that like they really want just one of them to be good.
Uh-huh.
It just happened that today they were talking about this particular case. By the way, this case really corresponds to a generalization of the Ross and Wagner result.
Okay.
And you wouldn't need backtracking to get the same result as Ross and Wagner. If all these suggestions are good,
Yeah.
then you just like follow it.
Yeah.
It's the same proof that they have. You get the same result, intuitively speaking as well, like nothing bad was suggested to
Yeah.
you. Fraction of states where bad things were suggested was just epsilon, so it kind of should work the same, regardless of whether you're branching or not, because the branchings are all good, so it's
Yeah.
immaterial whether you're branching or not. But it would be interesting if with backtracking you can improve upon that, or you would have this alternative where the only guarantee you would have is that the intersection between the suggested actions and the good actions is non-empty. So there is at least one action that's suggested to be good.
That's, I think, what I wanted to say.
Okay, with some probability, and then that would be like, wow, okay, like that's, now we are talking, that's more interesting. Yeah. So maybe that's what you wanted.
Yeah. So
It's
just
intersection.
just to be clear, the policy intersection over I star S is not this
This
With
has this
probability.
with probability, yeah.
1 minus epsilon prime.
Yeah.
Yeah, something like
That looks good to me. That's like
Oh,
an interesting,
Yeah.
Which is what Ali Reza said.
Yeah, at one point.
If there exists I, it's exactly like that.
Yeah.
Oh yeah, not for all I.
Yeah.
I think, well, we'll have to try this and see if the same proof holds and see what happens. Yeah. Anyway, that's what we managed to do.
Yeah.
And we're out of time. Thanks so much.
You know, good direction.
Yeah.
Finally, RL is in the picture.
Coming back, yeah.
First time.
Is it?
I think so.
So sad.
Can we use the camera?
Oh, I should have. Okay.
Oh, there is one here, zero.
There's another.
Four people.
I'm locked here.
Yeah. What if we had razors that like had a cleaning fluid?
We have better pens. Those are the pens. This way.
See, the title is not that important.
Whatever.
No, it's
I think you're using
Yeah,
a
that's-
pencil.
It's not there. This one is looking. Is it
the,
real?
yeah. Forward linear, right?
Oh, it's good.
Oh, two bars, two bars.
Ah, some uncharted territory.
Yep. Hello all. So this is a topic like beyond off and square, and we'll discuss everything about it. It's not discussed in the class until yet, so
Is it paper?
well, it's not a paper. There's like multiple papers working in this research direction. It's like a general problem with transformers, and we'll try to motivate the problem first, and then we'll see what we do. And yeah. So linear attention is a research area that's been popular since like 2020. There's like multiple research papers coming out since then. And I'll try to motivate the problem, but the main issue is that transformers, like the main language models that we use nowadays, even both encoder and decoder models, the internal mechanism is like full attention. And that is bottlenecked by big of n square, where n is like the context length that we use in the transformer networks. And in terms of both time complexity and memory complexity, we need to have like O of n square bounds so that we can actually compute that. And it's kind of a major problem, and a lot of research has gone into that, and we'll see why that's bounded by n squared. So if we actually
But
see
actually
it,
lower bounded by n squared. Not upper bounded. Lower bounded, right?
yeah,
Like currently, that's the problem.
it-
Because big O is like, oh, it's upper bounded, so it could be linear, but it's not. It's omega.
yeah,
Sorry. Just rambling.
it has to be omega.
Yeah, I mean, no, like your title is right, but
Yeah.
like when you're talking about it, then
Okay, sorry.
it's alright.
It's upper bounded by n squared.
Like, that would be okay, because linear or constant
Yeah,
is
lower
upper
bounded, yeah,
bounded
sorry,
by n
sorry.
squared too, but.
Sorry. Okay, let's say this, we have a vector embedding, which is like the word embedding plus the position embedding, and this kind of gets translated to linear transformation for key, query key, and value products, and then all of them go into an attention block and the transformer layer, and we have multiple of these layers. And then the output of this goes to an MLP, and we get the same embedding size right here that we get, and then all of this has to be then mapped to a softmax layer. That's how, in general, transformer works. But then a problem is that if n represents the context length and t represents like the vector embedding for each token size, the query key values are all bounded by n B sides. So generally how attention works is like it's a function of Q, K, and V, and the actual computation is like softmax over the query and K transpose under root D into the vector. This is like how sort attention layer works, and then the MLP layer is like a function of X and the parameters theta, and you actually just multiply them across that dimension and get an output. And mostly the problem is that when you actually do a linear transformation for this attention layer, you multiply the query and the key matrix transpose, so the dimensions are n cross d, and this becomes d cross n. So when you actually multiply this, becomes like the singular dimension, and the complexity is like lower bounded by this n squared, so the complexity of the attention layer comes out to be n squared d. And when this goes into the MLP layer, you're actually just multiplying across the vector dimension, and you have to do it for all the context tokens. So the complexity of the MLP layer comes out to be n into d squared. So overall the complexity is n squared d plus n d squared. In general, how normal transformers work nowadays is that the d dimension is somewhere around 8,000, but then the context tokens that we see are somewhere in the range of 100,000 or even more. So the overall complexity of the decoded only transformers, or the transformers that we see now, is bounded by big of n squared, because that dominates all the other terms. Yeah.
But then after you predict the first token, you cache all the keys, and then it's only when you're
We'll talk about
over.
it. So this is like the lower bound for the transformers is n squared in both time and memory, and why it's bad, because then you have to do matrix computation, and then when you're actually doing the training, you have to do the whole matrix computation, and then also save the attention matrices for all the layers, so that you can actually backprop to that. So then that also adds a computational overhead during training. And during inference, what you actually do is for example, you have an n cross n matrix, and then you kind of do a caching of this. For example, if n tokens are generated and you want to generate the n plus 1 token, you cache this and you only try to compute these tokens that would compute like the whole n plus 1 and the n plus 1 matrix for the attention. And this is generally done in KV caching, but even with that during inference, it actually is a bottleneck such that it is like bounded by n, so the computation is still dependent on like the token you're generating. For example, if you have to generate the 1,000 token, and if you have to generate the 2,000 token, the computation is dependent on the token that you're generating. So as the context length increases, it actually increases the memory and the computational overhead that you have. And this is like a problem that's been trying to solve in the research area, and there's like multiple directions that people are following, and we kind of, mostly our project is around literature review, and we kind of read like a lot of papers around what people are trying and what directions they're taking, and we kind of did some empirical results about a different thing that we could try maybe, and then we'll probably go over that. That is based on something similar to the Informer, and we'll go over the Informer paper as well right now. But yeah, this was like the motivation of the problem, and then we'll kind of overview the literature review that we did, and then we'll focus on the one paper that we're talking. So across literature since 2020, there are like multiple ways people have taken. One is like sparse attention. That's like a simple idea, but it has empirically proven to be very effective, and that's like the base of all the reasoning models that we see nowadays, including like Llama, Mistral, and all the reasoning models that we see. And the idea is simple. Instead of like full n cross n computation, you actually just use a sliding window attention. So for each token, you actually just look to the 3 tokens to the side, or maybe 3 tokens to the right. And then as you increase the layer, because your information gets aggregated, you kind of, as you progress through the layers, the global attention kind of gets squashed into a single token, and then you can actually, for example, if you're here and your sliding window is this, at this layer you don't have context of what the previous tokens were, but then as you increase the layer, because these layers, like these tokens, will aggregate all this information in the next layer. If this token aggregates information from here, it kind of creates a funnel like this. So all the information gets propagated, and as you increase layers, you get the context over the whole context. So, but we probably won't be focusing on that, but this is like a major direction that people are following. The paper that we want to discuss falls into the low rank adaptation category, where instead of doing n cross d computation, they actually just empirically and theoretically prove that the attention metrics, the Q and K transpose and the softmax over that actual computation is actually low ranked, and the Informer will probably talk about that. I'll go into more details afterward, but just like one more direction is like completely different architectures. Instead of using a transformer, there's like state space models and XLSTMs, and people have been working on trying to making them more parallel, because the only problem with RNNs was that they're not parallelizable and the vanishing gradient problem. So a lot of research has been gone into XLSTM networks that are parallelizable plus some kind of state space models plus the MAMA networks, and actually all of the recent research is in this category, and people are trying to like overcome this by completely different architectures and kind of removing the transformer backbone altogether. And these have seemingly performed well empirically for like smaller models up till like 3B, 7B, and like this is an active research area, but for now we'll focus on this area, which is like proving that the attention matrix can be approximated with a lower rank matrix, and then what we did around that and possibly what our project would be about. So the low rank adaptation thing, it's like Lin-Farmer paper that we'll talk about is a paper from Meta in 2020, and what they actually do is for if A is represents the Q and K transpose and P represents the softmax over this K matrix, they actually do a singular value decomposition of this P matrix, and what they see is that generally a lot of the eigenvalues actually do not carry any information, and most of that information can be captured in like K dimensions. For example, it's like has this bend over here, and generally they say that in K dimensions almost 90% of the information is captured. So maybe instead of doing this whole full attention, you can actually capture that information in a lower rank matrix, and that can actually reduce the computation that you do and the overhead that you have on the bounds. So probably Tayyab will talk more about that.
So the reason we're talking about Informer is that we had we had an idea that, yeah, question.
Do you use factorization after or before?
Before what?
As in this encoding it training, or you first train and then you?
No,
No,
during
it's
training.
during training, you make it learnable.
I'll
So we'll probably go
go into more detail on what Linformer is. So basically the idea we had for the project was, so normally in attention, every word looks at every other word to compute the attention scores.
Sorry, what do you mean by Linformer?
So Linformer is this paper that we are now discussing.
Okay.
Yeah. So we had this idea that instead of every word looking at every other word to compute the information of like attention scores and stuff, what if every word has some knowledge of some oracle or maybe one global knowledge heap where it looks and all the words are linked to that knowledge heap, and every word has to look at that just one knowledge heap to get the information. So this would make the thing like computation of attention scores linear. And we implemented the thing and we found Linformer was like our thing was sort of a special case of Linformer. So this is why we are focusing like in detail on Linformer. So Arham mentioned that this attention matrix, like they proved that this can be approximated by a low rank matrix. And so what the computation of attention in Linformer happens is like they have this. So normally we have Q matrix. Q is normally n by d, right? And Q gets multiplied with V usually, and V is also K. And K is also usually n by d. But what they do is they project this K with the help of a projection matrix, and they do it multiplied with this dimension, and it's
yeah, it's k by n. So what happens is, this first gets multiplied and k gets projected into k by d. And q we already have n by d. And now q gets multiplied with this transpose instead of simply k transpose. And the output that you get is n by k. And if you observe the time complexity of this computation, it is going to be like n, d is the common dimension, and then the k. So it is nkd. Instead of n squared d, for this first matrix multiplication that happens in the attention block, it is nkd in len format. Now that there's another matrix multiplication with the V matrix, and so normally when this thing would happen, a softmax would get applied with all of this, and for the sake of like simplicity, I'll just not write that. And there's a V vector here that is also n by d dimensional, and they also project it with the help of a projection matrix, and this is also k by n, just like this E1, and this gets multiplied and we get this shape k by d, and then this is the qk, like this is the attention matrix, like the matrix of attention scores, and this is the value matrix, and this would get multiplied and you'll get a n by d dimensional matrix, and its time complexity is also going to be O of n k. And the thing is, like intuitively, instead of having an attention matrix of let's say n by n dimensions, you every like word, instead of having attention scores to all the other words, what they do is they sort of create this shape of attention matrix. Like every word has information present within certain points from which it takes to compute the attention scores, and then they do averaging over the value matrix. So yeah.
How do they choose k?
How do they choose k? So in the paper they ran some empirical experiments, and they like choose 128 in the paper, and it captured I think 90-something% of the eigen value importances.
How big was that? What k? One.
The context line, it's a paper from 2020, so in general it was 512 at that point, but then they low rank it to I think 128.
Tiny.
Yeah, it was I think on BERT at that time, Roberta model, so it was like 512 for the context length, which was tiny at that time.
Yeah.
But
Just like 4 times smaller.
Yeah, so this was one thing that they did, and the way they prove it is they use this lemma called JL lemma. What?
It's a favorite. John's only that shows.
we did not know about it.
Yeah. So what this lemma, I'll not go into I think looking at the time, but what this essentially says that if you have 2 points in high dimensional space, and if you go in some low dimensional space, then the distance between the point approximately stays the same. They have some bound on the error, like they show that, and they like use this lemma to prove that even though we are projecting these vectors into a low dimensional subspace, but the dot products will eventually stay preserved, and even with this like this attention calculation in like low rank setting would not be like very error prone compared to vanilla attention. So this is the idea of the len format. Now what we did is we sort of did a you can say like special case of this is that, so this is a let's say Q matrix, this is a V matrix, and this is a this is K.
K transpose. Okay.
Yeah. So I'll show like grammatically instead of going into too much math. So normally this is n by d dimensional, and in case of len format this was n by
D. Wow.
k was eventually
Little k.
yeah
120.
k by d.
Okay,
So
after transpose.
yeah, so what we do is we make it 1 by d. They use a random projection matrix to like convert n by d into k by d, we use a learnable matrix. I'll come to that. How do we get this 1 by d vector from this whole information? But eventually what we do is we get this 1 by d, we make k equal to 1 and get this thing. And similarly for value matrix as well, instead of converting it into k by d, we use our thing to convert it into 1 by d. And the way we do it is that in case of, so there are two ways. One is just like Lin-Former, you apply a projection matrix R and you keep the value of k to be 1. But the thing is, according to JL lemma, like if you want the error to be like low, k needs to be proportional to context length. So still there's
Slogan.
yeah. So it still comes out there. So we didn't prove our thing. So like I don't know how much error prone it would be, but we ran some empirical experiments and we got pretty good performance, even better than vanilla transformer and Lin-Former. So we'll talk about those experiments. But there are also two more things that we added apart from Lin-Former in this. We call it quick former. So yeah. So this is one thing. So we convert this this whole matrix into one vector. Similarly, this whole thing into one vector, and then we normally compute the, so n by d would get multiplied by this, and it would be this. So instead of one matrix of attention scores, where every word has information like information for every other word, we have this one vector where basically all the n words are showing their importance, which are relevant to the attention computation. So let's say this value matrix, when it will be multiplied by this matrix, instead of every word looking at like every other word, we have this like for every single word we have this single, like all these words have one information that they are contributing to the central source of information. I don't know, something like that. Do you get it, or should I?
I do understand that you're reducing the k to 1.
Yeah.
And that's really drastic.
Yeah.
I mean, like my understanding of k was that, okay, like you want to apply some compression.
Yes.
And like, so n is a number of contacts, so there are all these different values that need to be provided as answers to the queries, and for matching the queries you need all these keys, but maybe you can apply some low dimensional projection to avoid the quality computation. I understand that. Going to one dimension seems really, really drastic.
Yes.
And magical to me if it does anything, because now you're completely, because I was imagining k is like log n, then it's like you have n log n that still scales with n, and mathematically we kind of know that that's possible to do.
Yes.
But if I decouple everything from n, now like intuitively speaking, it's like when I'm computing the value that I provide, it's like it's going to like the common deposit, and like it's merged with everything else, and it's just like one memory that we are all writing to, and then wow, okay, like that's
Okay.
not too much to keep around.
So there are two things. One, we are not like naively sort of merging it. We have two things. Like one, we have like the same matrix shape like key. We do dot product multiplication to each of different entry, and then we sort of stack it and again do dot product with another element-wise dot product with another learnable matrix. So these two matrices are learnable, and they are different for each of the different attention layer within the transformer. So even though they're sort of a,
Yeah, on the learnable idea, I think that that's really great,
yes,
and it's been always well documented in the literature that the GL, this random projection, is really horrible
yes,
as a way of doing it, and whenever you apply a learning method,
yes,
it tends to do better.
yes,
So I kind of understand that if you start to learn these projection matrices,
yes,
you should be able to do better.
yes,
I also understand that there is some structure there.
yes.
It still feels like wow, like you're going all in. It's like
Yeah, it's not really wow, but like it does really good on according to our
For small
experiments.
context length, maybe it will work. For large, we do not expect it to look at.
For the same for encoder, like only transformer architecture, like it does really good. But when you do try to apply this thing on cross attention tasks where you need cross attention, then it does bad. So this is a limitation of this thing. So for translation tasks, we try to run some experiments compared with vanilla transformer, linformer, it did not do well. But for all those tasks where we only needed the either encoder or decoder, then it did better than the vanilla
Yeah.
transformer.
So maybe to interpret what's going on, we have to remap how we are thinking about this query key value computation. Because in the old days, like when you have all these, like everyone's providing their key and everyone's providing their value, it's like associative retrieval from the past.
Mm.
And now, like, that is not the model. If k equals 1, clearly you are not retrieving as anything associatively from the past. The past is kind of like building some common memory up that kind of influencing things a little bit, but everyone contributes a little bit to that. And it's like a big mishmash of like just one big vector that kind of summarizes everything that is there to be. You are not really sensitive to the details.
Yeah.
And so when a query comes in, like a new guy comes in, then this global memory can be somehow accessed, but like you should not think about it as like you have detailed local memory. And I guess for tasks like you would need to count the number of characters in blah blah blah, like this would not do anything, right? Like it's hard to believe that you have enough dimensions to, like I scale up the inputs and yeah.
But if D is growing with N, then maybe it's okay to have the one dimension.
Yeah. Right, D can take the role of
Yeah.
N. If
And we have a-
D becomes log N, then
Yeah.
okay, we are in the realm of Jones Melinda shows and you win again.
Yeah, but then
Maybe you can prove that.
But then you can say you just have one dimension.
That's right.
It sounds good empirically.
Yeah.
Okay, we did something with D as well. So normally, Aram mentioned that the time unity of transformer is also this bounded on D squared. So you cannot drastically increase D. There's a bound with D as well. And we also, at the start of the transformer, after doing the position embeddings, we sort of run convolutions on the, like convolutional filters on the, let's say the n by d dimensional vector, and convert it into, okay, this is naive, but we convert it into n by square root of d, and then we run all of this attention stuff, which is already quick, and at the end, before actually, let's say, passing on to the prediction head, we again run some convolution filters. So we go borrow this idea from how the GANs work, like they compress stuff and then decompress. So we again run some filters and increase it back to n by d, and so this is another difference. So this was not like simple attention change.
Right.
This was also another two things. We call these boosters and feeders.
Oh man, there's everything.
And the thing is, we didn't run ablation studies. We don't know whether this is useful or not. Maybe it's not.
Right.
Like we are just compressing and decompressing. Maybe if you don't compress and run the same attention, maybe the linear attention that we propose, maybe it's better. Maybe it's not. But
Have people been trying to reduce the computation of MLPs?
No, not that much. Because it's mostly bounded on the context length and the attention matrices. So mostly the work is going into.
I mean, if like 99% of the work is done on the attention, like you don't care about MRT
Yeah.
until it starts to matter.
Well,
At the moment, that's where they are.
yeah. But then I'm just,
The idea sounds a little bit related to the state space models. No? It's like you're building
Yeah,
this
yeah.
state
Yes.
and retrieving
Yes.
from the.
yes.
Yes,
Have you
it's
seen
one-
if there's actually any connection? Like.
Like they also use a convolution to actually compress information in the states, because the normal structured S4 models, they use that convolution to actually make that recurrence parallel. Maybe.
So, yeah, in summary, the quick former thing that we sort of say, it has three new things. One, it has, you can say, let's say, quick attention, which is a special case of linformer, and then it has the convolutional filter stuff. two different things that we did to the architecture, and evaluation was on 3 tasks. One was GPT only task, like we ran next token prediction on Shakespeare literature, and compared to vanilla transformer, the perplexity of this thing was better. But again, these are low fidelity experiments. Like, we don't know how much these would scale with big data, but
Right.
yeah. So one was the language generation task. Ours was doing better than vanilla transformer. Second was one task, like sentiment classification, where we only needed the encoder architecture, and we compared for that task. We compared with linformer, and we were 3% better than linformer, and we didn't compare to vanilla transformer. We didn't find time to run for that, but compared to linformer, we were better. And third, for language translation task, we were horrible. Like, coming from n to 1. I don't know.
Is there any randomness in the process? As in, these 3 could be higher or lower?
I mean, other than like initialization of these convolution filters, and maybe, yeah, I don't think anything else.
And do you know if the results change if you change the initialization? As in,
No, we didn't find
Okay.
it.
okay.
How big is the model that you're training?
So this was 6 layers. D was small. It was, I think, 512, and like, it wasn't very big. Like, low fidelity
Million.
experiment.
Couple of million parameters.
Yeah, it was, I think, 65 million something. I have to check.
So how do you map it to 1 again? 1 dimension. How do you make K equal 1?
Yeah, what are the tricks?
Yeah, so 2 things. Like, no tricks. Like,
No tricks. Yeah.
so let's say there's
Exactly.
this is
I
a
like tricks.
let's say n by d dimensional vector. So let's say this is key. So there's a learnable set of parameters. So let's say I can change this. So let's say it was 3 by 3. There's another matrix. First, you like element wise dot product. So all these black elements are learnable, and then you squash them, and then you get a vector. And then again, there's also a learnable vector. So yeah.
What is squashing?
Adding.
Okay.
No averaging, adding.
Okay. But you have n times d learnable parameters. How many learnable parameters you have? I got confused. Like, you said that like there is a matrix that overlays the n by d matrix.
So right
These
now,
learnable elements, that would be a lot of learnable elements that would scale with n, that would defeat the purpose. So I'm sure you didn't mean that.
so within the attention, to reduce the size of the key and value matrices,
Right?
this is what we are using.
So, okay.
So it does not scale with n. Like, you can increase n.
So normally people just use a key and a query matrix, multiplies the vector, right? And then you record the result, okay? The output is d-dimensional, and that's why you have n positions, n by d outputs, right? Okay. So you do something to this. What do you do to this?
Yeah, so this is what I'm saying, that there's a learnable matrix,
Yeah.
the same shape as n by d for query and key.
So there's n by d parameters?
Yeah, how many parameters you have? Like
Yeah, so-
normally in
okay,
the
okay,
query
so-
matrix
yeah.
you have d by d, let's say.
Yeah.
And the key matrix you have d by d, and that's different than the q and the k matrices you're talking about here, because they are expanded on the data. They're the learnable small matrices, and you have the same number of learnable parameters.
Yes.
Let's say d by d for simplicity. And then, so how does that work?
So there are 3 cases. I get the point that you are saying that if you have all these matrices in each attention layer, and it would like expand with n.
I didn't even make that point, so it's like,
Okay.
yeah, just forget about our comments, just explain what you're doing.
Yeah. So for one layer,
Yeah.
you have Q matrix and V matrix. Sorry, V matrix and key matrix and value matrix. and you want to compress it, right?
Okay.
So in each layer, there's addition of 2 multiplied by n by d parameters, and
No.
they are
Not parameters. Like values that you compute,
Because like
maybe.
what as Chava was saying, right? There is like you have n like d-dimensional vectors that are representing your input stream, and then each one of those n things is multiplied by the same key and value matrix. That's d by d, and then that produces a new
Matrix,
And
n
you-
by d
yeah.
matrix.
yes.
Yeah.
But there's just one key matrix that's d by d and one value
So
matrix.
the number
that's
of
d by d.
parameters, we don't call it n by d.
Hmm.
We say that the number of parameters is d by d.
Hmm.
So I am sure that you're not saying that you have n by d parameters. So if your complex length is 1,000,000, then you would have 1,000,000
Yeah.
by 8,000 learnable parameters.
I think
No.
then it reached the point.
Yeah, that would
Yeah.
defeat the
Yeah.
point. You don't mean that,
Yeah.
but okay, then explain. Like you have this graph
Hmm.
explaining what's happening.
Hmm.
Vector comes in, there's a Q matrix, K matrix, V matrix, those are D by D matrices. I'm like, okay, so repeat this for n positions and then you get the n by D. But like, just for one position, this is the computation that's happening. Like, what's your computation? What did you do at one position? Like a token came in with its embedding, what do I do?
Okay, so I think I'll explain from here. So let's say a new token comes in.
Yeah.
Then this is query. So let's say previously it was n minus 1. Then at the next step it is going to be n cross d.
Yeah.
And then similarly my key matrix would be n by d originally without anything.
Yeah, yeah.
And this would be okay. And this is also going to be n by d.
Okay.
So what we do is
You just sum up the rows.
we sum up the rows,
Okay.
like convert it into one vector, and then there's a learnable, like
It's one row. Because then
This
you have
purple
one by
thing?
D. Yeah.
this is a learnable parameters, set of parameters, and they,
What is the length of that vector? How long is that vector?
this one,
Yeah.
this would be 1 by d, I think.
One by D, so
Yeah.
D parameters,
Yeah.
okay?
And similarly in case of v, it would be like this.
So you're just, yeah, we had an M by D matrix, that means that it has n rows, each had D elements, you're summing the rows, it becomes a row vector, okay, you made it a column vector.
Yeah.
And you have that many learnable parameters, I don't know
Yeah.
what those parameters are doing, what they're doing.
Okay, yeah. So this thing, this would be different for each attention layer.
Sure, but
Yeah.
like, what do you do with those parameters?
The previous one that I showed,
No, this new parameters that you're saying, yeah, there's a D-dimensional parameter vector. What does it do?
so it just like element wise dot product and nothing
Okay.
else.
Alright.
So this is what I'm trying to show here. Element wise dot product.
Element
I
wise
mean,
what-
product,
Element wise product.
Yeah.
not dot product.
Not dot.
Because then it would be just one number that comes
Yeah.
out. That would be probably too
Yeah.
little.
Similarly, yeah.
That would be like ultimate reduction. Yeah, yeah. Okay, okay. Is this really important to have this? Because in the query, sorry, the key and the value matrices, you already have learnable parameters. So it's like, this is like another set of learnable parameters that kind of plays the same role, like,
Yeah.
do you really need it?
So the intuition we had was that if you like sort of naively compress something,
Yeah.
so you're losing information. So
Yes,
let's
definitely.
Yeah. So this was the attempt to. Of course, we are not avoiding it, but something.
But
This
why
is not even a random projection, this is like summing it up.
Yeah.
I thought you would at least project it with like a weighted sum, not just a sum.
But I think that the point is that like if you decide about the way you're projecting and then you are
Yes.
training,
Yes.
after you decided how you project, then the architecture has degrees of freedom to deal with your projection.
Yes.
And so it's not like an afterthought, but like you already projecting. Okay, I guess the lean former people do the same with their unknown projections. And you are like, okay, like let's just go extreme k plus 1. So I don't care about this thing, but like in the projection, the random projection, I will have learnable parameters.
Yeah.
But they're just scaling the values. So it's, yeah, maybe it's doing something, but yeah, okay, I
I think
understand.
the next step is to actually sort of
Experiment a little bit with how the results would change if you go back to the informer, change the different k. I
Yeah.
guess like those guys must have run some experiments with different choices for k.
Yep.
Because yours seems to be like just an extreme choice of k, and okay, you're not, and you are learning the projection, but like your
Yes.
case is really extreme. This
Yes.
is a one-dimensional thing.
Yes.
You're not really learning much about the projection because
But are they actually learning the projection? I don't
yeah,
think
they're
they are.
not, because they are summing up. So there's like the all one vector that they decided to use as a way of projecting things.
Mhm.
But and then there is one scalar that they are kind of post multiplying with for each of the projects. So maybe, yeah.
Maybe there is a better way to do this. I don't know. Yeah.
Well,
Probably there is
I-
always something better that you can do, but yeah, it's really interesting that it still does something. It's a little bit unexpected. But you could take the projection matrices and just make that learnable, and then for different values of k,
Mhm.
and just learn it together.
Mhm.
And common wisdom would say that that should work way better.
Yeah.
And then choose k, maybe not that aggressively, but like medium aggressively, and then maybe things are going to improve. It's interesting.
I have so like as Chapa said, like the learnable parameters are just scaling the sum of the rows, right?
Yep.
So have you seen the effect of this, like just doing the summation and not using any learnable parameters? Like
No. We didn't try any ablation study. Like we had this idea, we just implemented it, worked on one or two problems.
Sleepless nights. That's okay.
But yeah, I think this is these are low fidelity experiments. I wouldn't say like it.
Yeah.
I don't know if this would work on a lot of data. And secondly, we already know for cross attention it does not work.
What does fidelity mean? Like the English word. What does low fidelity mean?
I think low fidelity normally means like if you have a transformer architect, instead of training it on GBs of data, you try to compare, let's say, with some baseline on 100 MB of data. I don't know what it means in English.
English it means faithful.
Oh, so it's not the same as the English meaning.
Yeah.
What English it means what?
I think like faithful.
Fidelity?
Like the multiple.
Yeah,
So
I
it's
think that this is like, it became a technical term that people just mean small scale experiments.
Yeah.
It's a fancy way of saying small scale experiments.
Yeah.
And what was perplexity? What is this measurement again?
So
Yeah, this would be-
perplexity
That's
measures
what
the-
you makes you perplexed, but
Yeah.
No, I started this in
like the quality of your language generation. Like it depends on the probability of the tokens that you are generating. It
Log
measures
loss.
how probable are they.
log loss. Log loss.
Yeah.
Oh, really?
Yeah.
Yeah, average log loss.
Okay.
All these new words. Well, language people call it perplexity because it's like intuitively it's the branching. It's like how branchy you are compared to like the source. If you're equally branchy, then it's gonna be good, and like, yeah, otherwise it's not. Like cross entropy, blah blah blah. Same thing.
So yeah, I think this was a project. Also for the sake of project, this was one thing that we wanted to try, but like we will definitely take it on, and we have done quite extensive literature review and what people are doing. This was one directions that we tried to like play around with, but yeah, I think this is an interesting thing.
Is this LoRa?
no, that's
For fine tuning.
training. That's for fine tuning mostly. You just
Is that what it stands for? LoRa? Low rank adaptation?
Yeah, yes. But that's
It's
more
not the
like-
first time it occurred to people.
Yeah. Because they actually do that a lot.
That's a patching.
Yeah, you first retrain the model and then you just append some new weights apart from the linear layers that you actually have, and then you only train those parameters. So it's like,
So that is fine tuning domain. So this is like training stuff, retraining.
Like a perturbation to the base model,
Yeah.
and the perturbation takes the form of the product of two matrices, which guarantees that you have much fewer parameters that are trainable than the total number of parameters,
and then
right?
LoRa applies mostly to the MLP layers, like the linear layers. You just add some new weights and just train those.
They don't do it with the attention stuff?
In the like the QKB linear transformations, and then on the actual MLP, I don't think
They do it on the attention as well, right? Laura, so basically they decompose each of these into the same, like how you mentioned, like the two matrices, low rank matrices, and then what they do is they fix the weights of like you can decompose delta W to W plus 2
Yeah, I think
matrix,
the-
and
the-
then
the-
you don't freeze your weights of so your delta W is fixed, and you only train these two matrices A, B, so that it's less number of parameters than retraining it.
But do they apply it?
Yes, on the attention as well. All Q, K, and B all are broken down into this sort of.
You know, they apply it here, right, on the linear layers.
Yeah.
Alright, anyways,